All right, so let's find, here we go. So Zyzel, which is one of the producers of cheap routers and such, I've had a few of them, they have got a serious flaw, which sounds like good, clean fun. You can authenticate as administrator by just adding 2 characters to the username when logging in, and they're not telling us which 2 characters it is to try to keep it secret. I think this is the one. They ignored them, and then they eventually went to the Department of Homeland Security, and they eventually got them to pay some attention. Anyway, I think, yeah, this is the one. All you have to do is inject 2 characters into the username, and then you can execute command execution on the server. So that sounds like good, clean fun, and it sounds like it would be pretty easy to just try all possible characters until you find it. So if anybody has Zyzel hardware, it might be fun figuring out what's going on here and getting this to work. Magento is a popular online payment scheme, and they have a plugin vulnerability. I see a lot of Magento and capture the flag contests. I think it's quite popular in the business world. And this one lets you manually insert a payment notification request without real payment. So you could trick it into thinking you had paid when you hadn't. And this is a PHP-based vulnerability. I'm surprised that people are happy using this thing in PHP. PHP has a very bad security record. But anyway, there is a patch out for this, and I guess it's all right if you keep patching them enough. Android malware can steal 2-factor authentication codes, which is this Google Authenticator was published and expected to be a very secure solution. It's supposed to be a lot better than sending the codes through SMS, but they're able to steal it with malware, which is strange and interesting, and I wonder why they're able to do it. But apparently this product does not yet exist. It's announced as an upcoming feature in Cerberus, which is a commercial product sold to criminals to attack phones. And they expect this variant is still in the test phase, but will be released soon. So I would be interested in how it manages to steal those Google Authenticator tokens, because I thought the whole point of Google Authenticator is that they're really being careful and not leaving this data just sitting in RAM that can be accessed by other processes or anywhere foolish, easy to steal. But apparently, they claim they have some way to steal it. There's a vulnerability that lets you decrypt some Wi-Fi packets. There have been a few of these. They're quite limited. I haven't panicked and decided we have to give up on WPA2 yet. But anyway, what this is after you do disassociation, then the encryption key is zeroed, and some small amount of packets after that are sent with an encryption key of 0 and can therefore be decrypted. So this reminds me of another vulnerability that came out about 6 years ago about WPA2, where under certain circumstances, you could arrange to decrypt a small number of packets. So it's not perfect, and they say upgrading to WPA3 will fix it. So that might be worth doing, but I wouldn't panic for this. It sounds like a relatively weak attack. And here, I'm quite interested in this tool, because what this does is it's a post-exploitation tool in PowerShell that steals passwords from RAM. And I did this years ago. I did this at Hope. When I did it, you could just use a Chrome browser and log into something like Gmail, and the password was just sitting in RAM. And after that, Chrome seemed to encrypt it. But here they're finding Dropbox passwords, Gmail, Jira, Xero, Slack passwords. So apparently a lot of products still have the password somewhere in RAM where you can find it. So it'd be worth looking at this and finding out how they do it. All these products apparently do store the password someplace in RAM in plain text or in some reversible form. So that sounds like a fun product to test out and to study more. San Francisco now has a state of emergency over coronavirus. All I hear on all the news everywhere is to freak out about coronavirus, and nobody seems to have any clue what we should do. It certainly is notable how unprepared we are. I got a funny cold, and I didn't bother going in to get tested because I read in the news there's no testing available in America. And Liz just got sick and went to the clinic, and they ran out of sanitizer, they ran out of face masks. So it does seem like we are woefully ill-prepared if people actually start having a real coronavirus spreading. I assume what I've got is just some kind of lesser flu that's spreading among the teachers, but I don't really know. And I guess I can't find out, and that does seem a little strange. But anyway, now we have the vice president in charge, so all this will be straightened out soon. Anyway, what is this nonsense? Okay. So the Shark Tank, I've never seen it because I don't watch TV, but apparently an investment show, and this woman lost $400,000 in a phishing scam. They sent an email saying you owe someone some money and managed to get the money transferred before anybody noticed. So it is a very common attack, a very simple attack. Just send an email and ask people to send you money. I've been hearing more and more of that happen. So these guys want me to pay for a membership. That's not likely to happen. Let's try a different browser. All right. So I thought this is fun. John Strand, a penetration tester. I have to see if there's any way to get this garbage off my screen. Okay. He does physical penetration tests, and his mom thought this was great. So he got his mom to go do the penetration test. And what he did was, she was not a technical hacker, so he just gave her a bunch of rubber duckies, which are these USB sticks that have scripts that run on them when you plug them in, and just said, go into this prison, a correctional facility, with a story. And she told them that she was doing a safety inspection for biological safety, which I think she had done as a job. So she was checking their kitchens and storage facilities for food and stuff. And that was, posing as a state health inspector was enough to convince them she was okay. And she just wandered in, and they let her in rooms, and she just plugged these USB things in, all the computers she could find, and it totally worked. So anyway, it's kind of fun to read. I think a lot of people love the glamour of pen testing, that you actually go perform real burglary and don't go to prison. So this one I mentioned yesterday in the other class, a fairly common thing. A couple of people, security experts, have written about this so far. Is you live in an apartment building, you come home and you just find a notice on your door saying your apartment building owner has decided to fill it with IoT devices. So now they will have like a burglar alarm controlled from the web, and a door lock controlled from the web, and security cameras and thermostats and everything. And I suppose this is so they can make sure the thermostat is turned off and try to do something about burglars and stuff, whether you like it or not. But a lot of people are nervous about this who are security experts, and he talks about how he complained and said, you know, I want various exceptions to this, and they had a good answer. Whereas when Hack for Pancakes did it about 6 months ago, she just got stonewalled and lied to, and no help from her company, and sort of had to force them into letting her out of it. Anyway, it is true that all the troublemaking you make as a red teamer and a security professional, which I've certainly done a lot of, slowly does erode people down. I sent out a ton of vulnerability requests, and I used to get less than 2% of them would ever get fixed, and most of them wouldn't talk to me at all. Now it's up to more like 10% that at least talk to me and have something resembling an intelligent answer, at least telling me something like, we're forwarding that to a security team and we'll do something about it. So people are slowly waking up to the fact that there is something called security, and you really should be paying some attention to it. And you shouldn't just install a bunch of weird remote controlled junk in people's houses and expect them to just go along with it without complaining. So here's a face recognition company, Clearview, which scraped the web, Facebook, and many other sources, and just got all these faces and then putting in a facial search engine, which the police say has been very helpful to catch kidnapped and exploited children. But it's also, there are serious privacy concerns. And now they have leaked their customer list by just not securing it properly. The details aren't clear, the technical details, but it is interesting. Many people are arguing about this. This practice is apparently legal in America, as far as anybody can tell, because we don't have much in the way of privacy legislation, although the way they got it did in fact violate Facebook's terms of service, whatever that matters. But anyway, we're living through a big argument about privacy and use of online information by police and also by private companies. The current situation is the police have some restrictions, and the private companies seem to have no restrictions at all. There are a few laws, but they don't seem to actually do any good. Anyway, I thought this was fun. They have classes now to teach older people to spot fake news, because it is mostly older people who fall for fake news and forward it. And they say that's because they are used to the clues for fake news being like the type where the newspaper is sold in the store, so you know which ones are tabloid and fake. And online, there aren't any such clues, so they're teaching them about sites like Snopes that will detect fake sites and other fact-checking sites, and how to be suspicious and how to quickly check to see if something is fake, which seems like a great thing. And we should have classes like that around here. If we don't, it'd be a very good thing to do. Anyway, so here we are. Let me just, we're at 129S here, and we are here. So this is 227. We're going to talk about session management, and people are hopefully working on W210. All right, and I moved the quiz, so it's not due till next week, because I had planned to have like a guest speaker today, but I don't have a guest speaker lined up, so I'm just going to have a normal lecture. So here we are. We'll talk about session management, and it's a few new things to add to what we talked about before. So since HTTP is fundamentally stateless, it forgets who you are every time you make another request to load an image or some JavaScript or something. Someone says, look at the ads. Well, I guess I missed whatever that was about. Anyway, so you get, all right, so if you, it has to have some trick to remember the session, which is generally cookies. And so this means if I can confuse that system, I can impersonate another user or elevate myself to administrator and so on. Sometimes this is very simple. One very common thing, which happens a lot, is you'll have something like a college, like ccsf.edu, and then you'll have something like /grades, and then you'll have something like ID equals 111.222. This is something a student got in big trouble for finding a few years ago at a college. Well, it's funny, the browser absolutely refuses to stop showing the favorites bar, and right click doesn't work. Yeah, okay, there's always something wrong. Anyway, so students would see a system like this, and then they could just increment the last digit to 3, and they'd see a different student's grades, and 4, and they'd see a different student's grades. This happens pretty often, things like that. And that's one of the many ways you can do this wrong. So there might be an obvious token that can just be incremented. This happened to me, simple cross-site request forgery at DEF CON. I went to Gmail and used it at DEF CON because I thought it was using HTTPS, but it wasn't. It was only using HTTPS to log in. And then after that, it would switch back to HTTP and send a session cookie in plain text, which could be stolen and reused. And you could catch it with any of a variety of tools. And that year, some people had written these specialized hacking tools just for this attack called Hamster and Ferret, which they used to get into my account. And I was on the wall of sheep. Wall of sheep is what they put you on at DEF CON if you use an insecure login, and they're able to get in your account. So that was educational. And anyway, so you have to have a state. The HTTP protocol itself doesn't have any way to keep track of who you are, but we do want to be able to log in. So we go through some process called the login, and then we somehow have to remember that we are logged in as one person. And then at some other time, we can log out and log in as somebody else. And that's all patched into the system without being built into the fundamental protocol. There are other things like shopping baskets and so on that have to be stored on here or remember something from one response to the next. So when it's time for you to remember something, the server gives you a set cookie header, which will now set something with a name. This one is called ASP.NET session ID and then a value. And every subsequent request that your browser makes to the same domain will repeat all those cookies. So it sends them with every request, assuming that the reason the server put them on there is because they're going to personalize the response. So that's the game. So there's two general categories. One is if the cookies are generated in an insecure way, and the other is if they're handled in an insecure way, so you can steal them. So some platforms automatically generate tokens, and a map might not really use it. So you might want to find out which cookies actually matter. I use Burke Repeater for this. It's good, clean fun. So you can go to a site like Hackazon, log in, and then you have 3 cookies here. And you can now just delete these cookies one by one in the repeater until you're no longer logged in, and you can see what happens. So it's easy enough to do, and you can try it for everything. I've tried it for Comcast and Amazon and everybody. This, I guess, is Amazon. I think is real, yeah, real Amazon, I think. And there are a lot of cookies, and I found out which one of these actually authenticated you. So it's pretty easy to do with Burp Repeater. All right, and so I got it down to this. Nothing was actually needed but the X main cookie, and it still knew who I was. All the rest could be removed. So there are other ways to identify yourself. There's basic authentication, which is just a different authentication header, and digest and NTLM. These, again, pass credentials in every request, and they're not commonly used on the internet. They're commonly used inside Windows domains, but basic is pretty commonly used on the internet still. All right, and there are sessionless state mechanisms where it doesn't issue session tokens. Instead, it sends you a cookie that has everything you need to know. It just goes back and forth with you. And this is what ASP.NET, Microsoft's product, ViewState does. It sends a whole blob of data to you, so the server doesn't have to remember any of it. And so you can unpack it, and you'll see things in there. You can make an array list with all these items, and they will all just be added to the view state here by array list. So this is the script on the server that would have created this stuff and stored many bits of information in the view state. And you can store anything in there: strings, tables, Boolean values, arrays, and all that junk is just bouncing off the client all the time. Now, the view state in early version was just a blob that could be opened up and altered, and that wasn't safe. So now it can be protected with a base 64 encoding and then a hash, including your machine's MAC address, so it knows who you are, and it knows that the data has not been altered. And you can't, therefore, since it includes the machine's MAC address, you can't even easily steal it and copy it and put it on another machine and use it. So it's pretty good. If you turn on all the modern features, this is a pretty good system. Anyway, all right, so here's indicators of these session-like mechanisms. You'll have long data items, 100 bytes long or more. You get a new item in response to every request, and the data is encrypted or signed. You'll see some structure in it, and if you try to submit the same item with more than one request, you can't because it's keeping track of something. Those are all clues that that cookie you got is not just an identity tag, but it is really got data stored in it. All right, and so then you can talk about how the tokens are generated. Here's a guy that made $15,000 by finding a way to predict the Facebook page reset token. I've talked about this before. When you do a password reset, the so apparently random number there was in fact findable elsewhere on the page. So he was able to generate password reset tokens for other people's accounts and get into them. So anyway, that's the game. So here's common uses. You send a token to an email address for someone to click that they can reset a password. You hide it in form fields. You use persistent tokens to remember that you've logged in, and so on. They're quite useful, but they all depend on that token being unpredictable, so nobody can guess somebody else's token. One common thing people do is use meaningful tokens. This looks like random numbers, but if you look at it, 75, 73, 65, 72, those are ASCII characters. And so this is just spelling out user equals staff and all this in ASCII. And so it would be easy enough to just change that to someone else. This is the dangerous kind of token where you actually hide data in the token. All right. And so people put in the username, an numeric identifier, email address, date timestamp, client IP address, common things people put in structured tokens. And you can encode them in a variety of ways. XOR just flips some of the bits. Base 64 groups the bits 6 at a time instead of 8 at a time to create a string of characters that'll be uppercase, lowercase, numbers, and a couple punctuation marks. We just saw hexadecimal ASCII codes. So if you have a token which has encoded real data in simple ways, then you can just do things like flip one bit at a time, and that would have a meaningful change, like just changing a digit in a number, like a user ID or something. So this would be an easy way to do this. And there's a thing called char frobber, which is what Burp does automatically in Burp Intruder to make these small changes in a token to see if you end up with a token that has some other meaning. It can help to make usernames with similar names, and we'll see one of these later. I've gotten to use many times where you just make a name that is very long, repeating the same letter. Anyway, look for correlations. So a series of repeating letters will produce repeating encoded characters. If using XOR, single byte XOR, every A will just turn to another character. Base 64 often has these equal signs in it. That's an easy way to spot them. It's also pretty easy to spot because it's always uppercase and lowercase letters and numbers, so it looks different than hexadecimal. Anyway, if you find a token that looks like it has any structure, you can just try modifying it to see if you have any other meaning. That's one way to detect this kind of flaw. So I've got some iClickers here, or these things are cahoots now. There we are. All right. And get a place to put the winners. All right, I'll give it a few more seconds. It looks like that's about enough. All right. So, what encoding will turn that string into that string? All right, that's base 64 with the upper end lowercase. All right, good. And what encoding will turn into that kind of thing? All right, that's MD5, where it has a fixed length that is that long, relatively long. It's, by the way, not intended to be reversible, although you can sometimes reverse it if you can guess this. All right. And what encoding turns it into this? All right, that's XOR, and you can tell because it's not hexadecimal because A is just 65, not 05. But when you have 4 characters that are the same and they turn into 4 bytes that are the same, that's a strong clue of XOR. Each character has just been modified in a predictable way. All right, and what encoding does this? That's just hex. A is 41 in hex, 4141, and lowercase letters are higher numbers like 75 in hex and so on. If you don't know them, you get used to them. All right, so Carrie Lynn. Silly. Okay, that's one I've seen before. I don't know who that is, but anyway, we will carry on. So, all right, so here's predictable tokens. It turns out, by the way, to be far more difficult than you might imagine to make a random number on a computer. Even the best people that try to make random numbers have trouble. So If you try sequential tokens, that's easy. Burp will just try adding the numbers one by one and tell you what they log in as so you can see them. And then it'll move the ones that match up to the top. So that's a handy thing. So you might find concealed sequences or time dependency or various kinds of weak random numbers. Now this sequence, it looks base 64 encoded, but if you decode it, it just turns into gibberish. But it is in fact a concealed sequence. This is called a linear congruential system. If you calculate the difference between sequential tokens, you keep getting very similar numbers. And what's happening here is it's just adding a constant every time and then keeping only the lower bits and letting it roll over. So it looks random, but in fact, it's just a straight line when graphed properly. That is a fairly common type of random number generator, linear congruential generators. And the numbers look random, but in fact, after you figure out what's going on, you can predict all the numbers by just knowing the first two. So you can write script that will decode it just by keeping numbers to the right, bits to the right, and adding a constant every time. Anyways, you can generate valid tokens here and so on. It's easy enough to repeat. You just can calculate 7 tokens by just adding this number and then just keeping only a certain number of bits on the right and throwing away the high ordered bits. Time dependency is another one. The left number just increased by 1 every time. The right number moves up by a varying value because it's just doing something like counting the number of milliseconds since you created that account. So again, you could pretty quickly guess somebody else's token by just adding one to your number and then adding some numbers to your time. And I guess if you try from say 50 to 500, you have a pretty good chance of guessing that time. So anyway, all right, so you pull the server and get a session tokens, and then you look for patterns like this. There could be any of these patterns. It's amazing how many people write systems like this. I've had students come to me and say, I'm writing a system, and how about I invent my own way of hashing passwords or something. It's amazing how many developers do this. That's why the most important thing you can learn about cryptography is don't write your own cryptography. You think you're smart enough, but you are not. Just use a standard technique. You'll be sorry if you make your own stuff. So Jetty is a web server that used linear congruential generators, and so you can predict them all the same way. Was one of the many examples of this happening. PHP used a similar system with linear congruential generator and a few other numbers like time. And Sami Kamkar, a famous hacker, wrote the tool to crack into those by predicting the random numbers. It is very difficult to make random numbers. That's why Dilbert eventually made fun of it. You can have a random number generator that just gives you 9 6 times. And is that random or not? You don't know. That could happen. It's actually not simple to decide whether something is really random enough. So anyway, you start with the hypothesis that it's randomly generated and then apply a series of tests, and you can then eventually show that there's a pattern and it's not random. Burp has a sequencer that will do this for you, and you can see it in some systems. The red bits are not random, the green bits are random. And this was something that happened to quite a few Microsoft products, like the early implementations of address space layout randomization. They had a random number, but it wasn't really very random. Many of the bits could be predicted. So you could in fact guess more often than you should be able to guess where it had supposedly randomized the location of data. And then there's encrypted tokens. This is another way people go. They will take something like the username or another information, and then they will encrypt it with a secret key and think that makes it okay. This is a very common mistake, to think that if somebody only has encrypted data, they can't do anything with it. In fact, you can often do interesting things with encrypted data, even if you cannot decrypt it. One common mistake is textbook encryption. The most common kind of encryption for beginners is electronic code book, where you just break the input up into blocks, encrypt it with a key, and each block you encrypt separately. So if 2 blocks have the same input, they produce the same output. So if you encrypt this image, it turns into this. Each block of solid color just turns into a different block of solid color, and so the patterns are still preserved. So here's ECB. Here's a token that contains a series of values, a random number, a user ID, a user name, and then a time. And then you encrypt it. It appears meaningless, but it's not. it's actually blocks of eight bytes of input encrypted. Now, in this case, none of the input blocks repeat, so none of the output blocks repeat. So you can't see a pattern here. But what you can do is you can just copy a whole block. So if you go here, I had a random number that ended in 992, and here I have UID equals, and the next line should have had the UID of 218. But if I just take this entire block and put it here, duplicating it, it's going to decrypt. So now I've got to a different user by just moving a block around, even though I can't decrypt it. Because this data is somewhat structured, I can just flip whole blocks around, and sometimes I will get lucky and it will create something meaningful. So now you can target UID equals 1, and I set up a project where you do this. This UID is 219, but if you make another account with a name that is shorter, you can make it so it wraps around. And how do you know to use a particular block? And of course, you don't. So you just mix them all. You flip all the blocks and try them all and see what happens. And if it has this flaw, then you will occasionally have an unexpected result like getting in somebody else's account. You don't know. So that's one defect of electronic codebook mode. Now the cure for electronic codebook mode, and the most popular type that's actually used, is cipher block chaining, where you have not only a key, but you also have an initialization vector, which you XOR with the plain text before encrypting it. So the key and the IV come in and you encrypt the first block. And for the second block, you use the same key, but you use the output of this block as the key, as the IV for the next. So this does improve it. So the apple encrypts like this. It just turns into meaningless snow. So it's generally considered far better. But it does have another weakness, which we can exploit. If you were to use the same kind of structured data and then encrypt it with cipher block chaining, again, it would look fine. But consider this. If I just change one byte of the ciphertext, perhaps by just changing one bit, then when it gets decrypted, this whole block will turn into garbled nonsense. But this block, it will only affect it through the XOR process. So the one bit I change here will only change one bit here. So now if I'm willing to accept the collateral damage of wiping out a whole block of data, the next block, I can make a small change in just one character. So again, I might be able to change a number or user ID or something. So Burp has a tool. So here's an example of altered values. You kill a whole block, but this changed to 8. Then you kill that block, but this one changed to 2. This P changes to Q. This B changes to an A. You know, you can make small changes that might be meaningful. Like here, the UID is now 226 instead of 216. So this might be another person's account. So it's the same thing. Burp has the ability to do this. It'll automatically flip each bit. You can set it up, and then it will just try them all. This won't take very many requests because you're not just one request per bit, and it'll just show you what happens. And most of the time, let me make this as big as I can. Most of the time, you'll just see DAF, which is the real user, but a bunch of them will be unknown. But in the middle, there's a few that actually hit other users, Peter, John, and somebody else, Peter and John. So 2 of them actually made it into other users' accounts because of this flaw. So you can't control what you're doing, but you can make changes which will fool the system into hitting other meaningful values. All right, another thing you can do, by the way, is often the encryption code is used somewhere else. So you might find a place where you can put in some data and it will encrypt it for you, and you can then replay that encrypted data. So those are other flaws that I've seen in encryption modes. And I mentioned before, one thing I've done in a lot of testing apps is make a user account that's 32 letters long, all the same. And then I look in the encrypted data to see if it repeats. And then I know they used electronic codebook, which a lot of Android apps do. Anyway, this is 7B. All right. before that, that might actually be helping my grader. Nope, didn't get it, okay. Maybe relevant. All right, anyway. All right, good. I think that's probably enough. I'll give it about 5 more seconds. All right. So, which encryption uses one block of data to influence the next block's encryption? That's cipher block chaining. One block is chained into the next block. All right. Which one can you exploit by changing a single byte? That's the cipher block chaining. Change one byte of input will change only one byte in the next block of output. All right. And which one do you get by exploit by rearranging blocks of ciphertext? Electronic code book, yes. And which token generation system makes replay attacks easy? All right, if you encrypt meaningful data, then you can just store the encrypted stuff and replay it to get back in, because you're just decrypting it at the other end. That's another reason why you should have something in there like the time or something random. Fortega might be a real name. Zoe is a real name, I think. And Gary Lynn. All right, good. All right, good. All right, I think we can just keep going. Let's go back to here. And, all right, then there's weaknesses in handling, which we've talked about. A lot of people think SSL makes your product secure. A couple of years ago, there was a voting product that tried to defend their security by just showing that their SSL certificate was correct, and they felt like that was enough to make them secure. And of course, it's not. It protects you only against one attack, which is sniffing on the wireless transmission or wired transmission. It doesn't stop other ones. So your token, if it is transmitted without encryption, of course, then it's easy to steal all over the place. Anybody on the local network or at the ISP or anywhere in between can get it. All right, but if stealing a user's password might not work. It won't do you any good at Google anymore. Google now uses two-factor authentication for everything. Everybody has these little YubiKeys, and they say since they did that, they've never had any phishing work at all. Because even if you steal somebody's password, you can't use it unless you also steal their hardware token. So this is a good idea. Now, if you can steal a session token after they have logged in and replay the token, then you never go through the login process again, and you can reuse their account. So it's another way to do it. As I mentioned, in the old days, Gmail used to let you log in over HTTPS, but then switch to HTTP and send a cookie, which could be stolen and replayed to identify you. So that's not good. And another thing is some people they assign you a session token, and then when you log in, they just add privileges to the existing token. This makes it possible to steal the token before login, or even perform session fixation, where I send you a link that includes a token. And when you go to visit the page accepts the token that I gave you, which I know. Hackathon actually falls for that, and I'll have that in the Hackathon project pretty soon. I've written it up, but I haven't published that one yet. Anyway, so another thing is the back button. If you have part of your page using HTTP and part of your page using HTTPS, and the user logs in and then uses the back button to go back to the unencrypted page, it might send the token up to the server without encryption on the HTTP page. That's why everything is moving very rapidly to 100% HTTPS, which Google did in 2012. And now everyone is being strongly encouraged to, starting about a year ago, browsers now warn you to just not use any pages that are not HTTPS for any reason, which is where we're all headed. And that will end a whole lot of the vulnerabilities we're going to talk about here. SSL strip is one of the many. If you take a page that ought to be HTTPS and I get in the middle and just serve you an HTTP version instead, it'll look just the same to you, especially if you're using a mobile device that doesn't let you see the address bar. And then you can log in and you don't know that your data is being transmitted to me unencrypted. Nowadays, modern browsers will warn you not to use any page that is HTTP for this reason, among many others. And Firefox doesn't like mixed content. That's been for even more years blocked, which is pages that have HTTPS, but they load some HTTP content. This is still pretty common because your ads from other companies come in without HTTPS and so on. But as I've been saying, we're pretty much at the end of this. I think we're living through a few year period here where everyone just knocks it off using HTTP at all. All right, so even if the app uses HTTPS completely, you could send them an HTTP link, and then you might be able to get a session token to go there over 443 if the server still allows any unencrypted traffic. A surprising number of servers, I've even had people request this saying, you should make it so I can come in over HTTP and then it will redirect me to HTTPS, which is an insecure practice, but a lot of people still think you should do that to make it convenient for your customers. Anyway, so just the way you detect these problems is you wander through the app and look at all the requests in something like Burp and watch where the tokens you get and watch where it transitions between HTTP and HTTPS. So Burp's HTTP history will let you see what's going on, and here it is getting tokens, and this one's staying HTTP all the time, but those are not common anymore. Right, if you put a secure flag on a cookie, the browser will only send it over HTTPS, and that's a good thing. And I had a demonstration. I don't think I'll bother doing it live here, but if you do log in with a secure-only cookie and then go to the insecure version of the page, you won't be logged in anymore because it doesn't send the cookie up, which is nice. And so when you set a cookie, you can just set this flag, secure equals true, and that will tell the browser not to transmit it. So you'll see this cookie has secure and HTTP only flags set, which means it will only be sent over HTTPS, and it will only be sent as part of an HTTP request, so it cannot be stolen by JavaScript. So the techniques we've been using in the previous couple of classes of running a JavaScript to steal a cookie won't work either. So those are good things to put on your cookie to make it stronger. All right. So you go to an HTTP version of the page and you can't get in because it's forgotten who you are. Anyway, the secure page knows who you are, but the insecure page would not. And an HTTP only cannot be stolen with cross-site scripting. So it's another good flag to put on there. Now you can specify on your server that it should always be served over HTTPS. And this is probably a good thing to do in this transition period when some people are still using HTTP. I think within a few years, this will just be the default everywhere. But you can add a header, HSTS, which tells the browser to always connect securely and not even let the user override this by giving them a warning. So only a small number of websites were using it as of 2018. But I think it's gonna not matter soon as everything's just 100% HTTPS anyway. Another less common problem is that you might have logs that are visible to the whole world because you haven't configured your logging servers very well. And then they might reveal things like you can go online and look for, I did this when I was showing you some Google Docs a couple of classes ago. There are ways to see online logs, and they will show information that might have tokens in them. Another thing you can do is if you put information in the URL, instead of putting it in the body part of a post request where it belongs, then it will also appear in the referrer value on the next page you go to. So if I can trick you into coming directly to one of my pages from an authenticated session, which is pretty easy, like a link inside Facebook or something, then I could get the referrer token to leak information to me. I think this is probably why so many email clients and everything, now when you click them, it'll have a special page pop up and say, you are now leaving Facebook, you are now leaving Gmail. I think they've realized they want to warn you when you're leaving the site. And so the referrer may have a session ID in it if it was actually stored in the URL, which is not the right place to store it. If it had been in a cookie, that wouldn't have mattered. So that's the referrer attack. All right, and if you allowed users to have two sessions open at the same time, then using the same session token both times, then this is a very strange thing to do. And this is the kind of thing you might do if you're actually encrypting meaningful data in the session. A session token really ought to be just recording one session between one client and the server. Anyway, so here's one where it decodes into a username and a number, but you can use the same number with a different user, which is another bit of flawed logic. All right, another big problem, which I found to be huge on the web, I heard about it years ago and did a big study of it, was sessions that stay valid even after you log out. All the logout button does is delete the local cookie and the session token remains valid. This is true of a lot of web properties. So I did a study of it years ago and found it true of American Express and many other services, Office 365, and I had a whole list of them at one time. So if I was somehow able to steal your cookie, then I can get in. If I'm able to feed a token to the user, which is then used when they log in and not changed, then I have your cookie because I gave it to you. If I use cross-site request forgery, I can trick the user into submitting a request that will send a cookie to my server so I can find your cookie. And once I get your cookie, I'm in your account and you can't get rid of me even by changing your password on many services. Logging out does nothing and changing your password does nothing. And there is no option anywhere for you to make the old cookies invalid. So the only thing you can do is close your account and make a new account to get rid of me, which is pretty rude. Now, another issue is cookie scope. If you set a cookie to games.samsclass.info, then it will be sent to every request to that domain or domains that add more to the left here. So foo.games.samsclass.info is considered by your browser to be part of games.samsclass.info, and it will send that cookie. But samsclass.info is not in the same domain as games.samsclass.info, so the cookie for games.samsclass.info will not be sent. So this means you can control it if you're careful. So if you set a cookie, you can set its domain, wapp.com, and it would then send it to wapp.com and bar wapp.com. All right. By the way, you can't set a cookie for .com. All you can do, the most general thing you can do is company.com. So if you have a company that has blogs and they set a cookie on blogs.com, each user creates a blog, and now that cookie can be stolen by anybody. So that's the wrong way to do it. The right way to do it is to define www.blogs.com for the main app, and then have each person have their own subdomain, joe.blog, sue.blogs, and then the cookies that they use cannot be sent to some other user's blog. In general, this is part of the very error-prone same origin policy in browsers, where the browser wants to know what domain it's talking to and then limit what it does based on that. And this turns out to be very problematic, but it is the security model that we are all using. All right. So anyway, then we talk about session management. So you want to generate strong tokens and protect them from creation to disposal. So the best thing is to have a large set of random numbers and not meaningful data in there, containing no meaning or structure. You should be aware that some random number generators are not unpredictable, and all the actual data should be stored on the server. The token should just be a random number, which tells you which record on the server to refer to. So here's things you can use to get randomness: the IP address, the user agent, the time in milliseconds. A common method is to take these things and then add a secret known only to the server and then hash it all. This is a way to get pretty good entropy. You should only transmit them over HTTPS and only over HTTP, not over JavaScript. Don't put them in the URL. When you log out, it should invalidate the session token on the server, so that token cannot be used again. They often recommend sessions should expire. The only people I've seen actually do this are bank websites. No one else is willing to do that. Not allowing concurrent logins also is something that only the highest security places will put up with. All right. and consider the code, the domain and path for your session cookies. And when you get tokens submitted by unrecognized users, you should cancel those tokens. Two-factor authentication is far better. Hidden fields are often more useful than session cookies because session cookies are sent in every request, even ones to some kind of malicious other page that you didn't intend the user to go to. So a better thing to do would be to define tokens as hidden fields on a page. So they will only be sent when they submit that one page. All right, you shouldn't reuse old session tokens, and you should always create a new token when you log in, not continue to use a token that was used for an unauthenticated session. And so here's how these per page tokens work that are recommended a lot in this book. You have a hidden token like this on each page. You should have a form, and it's got a hidden number, screen token, with just this long random number. And so on the next page, you'll check to make sure they really have that token. And this token is regenerated separately for every user. So now I can't steal a cookie and replay the cookie from some other machine and get in somebody's account. I really have to be the person you expected coming from the page you expected. This is how you can really control the flow of people through your app and make sure that attackers aren't sneaking in with stolen secrets. So again, you should watch for these invalid things, and instead of just forcing them to try again, you should alert users that somebody's trying to hack into their account, and then alert your server and your IDS system that this person is a bad hacker, and you should do something like block their IP address, or terminate their session, or so on. These are good practices, instead of just making some system that ignores errors and lets people try again so the attacker can just try over and over until they hit the right combination. So we're up to the last Kahoot. We bring it up, which is 7C here. All right. All right, I'll give it a few more seconds, but I think 12 is as many as we've been getting. All right. All right, what does HTTPS prevent? All right, that's it. You can't just sniff it off the wire. All right. What should happen when a server receives a request with a modified hidden form field? Terminate the session. That indicates that something bad is happening, and they should not be allowed to proceed without logging in again, because something is going wrong. Probably somebody else is trying to sneak into their session. All right. So what protects cookies from JavaScript attacks? Okay, that is HTTP only. You set the cookie with that flag and it will not be delivered in response to a JavaScript request. All right. So what should a logout button do? Should terminate the session on the server so that token is not valid anymore. All right. Now, what defense prevents users from clicking through an SSL warning? That's one of the things HSTS does. All right. And what kind of session token is not sent on every request? Hidden fields are the ones. Cookies are sent with every request. Hidden fields are just sent from that one page, so you know they came just from there and no place else. All right. Phil Fry, okay. Gary Lynn. I think Zoe. Indeed, Zoe. All right. Well, good. All right, I'm going to stop recording, and I'll leave the share going for a minute or two to see if anybody has any more questions.